Welcome to Ready to Derive. In this video, we're going to learn about interval and set builder notation. Now, while these notations are often used to describe domain and range, I find it easier to just look at simple inequalities and how to translate those inequalities into this notation. So coming into this video, you should be familiar with what an inequality looks like. This one says -3 is less than or equal to x is less than 2. You should also be familiar with how to graph it. And then I'm just going to show you the notation so you know if this is the right video for you. So interval notation would look like the one on the left, and set builder notation like the one on the right. Now, if you don't need to know about set builder notation, that's okay. We do lots of interval notation practice and you can ignore the set builder part. But since they are used interchangeably to describe, intervals or domain and range, it's probably good to see both. So without further ado, let's begin. To begin, we're going to graph x is greater than or equal to -3. So this is a throwback to Algebra 1. And if you recall, so -3 is, x is allowed to be -3, so we put a shaded in circle there. And then we put an arrow heading to the right because x is allowed to be any number to the right of -3 all the way up to infinity. And the easiest way to introduce interval notation is just to show it to you and then explain it. So this is what interval notation looks like. And just to explain what's going on, basically it's saying that x can be as low as -3, comma means up to infinity. So you go from low to high here. So from -3 all the way up to positive infinity. But you're probably wondering what these symbols mean. This is very important. On the left here, this is called a bracket. And a bracket means that the value next to that bracket is an included value. So x is allowed to equal -3. On this side, you should recognize that as a parentheses. And the parentheses means not included. And why is infinity not included? Because x can never achieve infinity. It can only get closer and closer. So now let's take set builder notation and have a look at this. So interval notation, you might at first prefer this because when you see set builder notation, it's going to look a little overwhelming, but I'll explain. So set builder notation looks like this. These curly brackets are what we use for set notation. So curly brackets, sometimes squiggly brackets, whatever you want to call it. And let me explain the symbol. So x is x, right? So this is saying that x, this symbol here, this E stands for is contained in or is an element of. So x, the values of x are contained in, now what's this R? This fancy R stands for the set of real numbers. Now, right now we know that we're dealing with just real numbers. What could that be? That could also be integers or natural numbers. But right now, if you see we're allowed to take on decimals, x can be -1.5, for example. So x is allowed to be any number in the set of real numbers. And then here, this symbol here, this vertical line means such that. You're probably getting the idea, the correct idea, that mathematicians don't actually like to write words. We'd rather translate everything to symbols, and I think we do that pretty well. And then after the such that, so x can't be any old real number. It has to still be greater than or equal to -3. And you might be wondering, well, couldn't we have just said x is bigger than or equal to -3? Well, yes, in this case, because we know that we're dealing with a number line. But if you didn't have that graph, you wouldn't necessarily know that you're dealing with a number line, and you have to specify, what set x is an element of. So again, to really understand this, we just have to keep doing practice. So now we'll practice heading the opposite direction. And now we have x is less than 2. So before we had greater than or equal to, now we have less. So x could be numbers that are less than 2, 1, 0, -1, that all works. How high can we go here? Well, x could be 1.9, 1.99, etc. Get very close to 2, but not quite achieve it. So we put an open circle over 2. To mean that 2 cannot be included, and we put an arrow going to the left heading towards -infinity. So what would interval notation be with? So remember we have a comma and we put the lower number on the left and the higher number on the right. So the lower number, well, it's heading towards negative infinity. It can't achieve that, so we put parentheses there. And x can go all the way up to 2, but it can't achieve 2, so we use parentheses again. So no brackets in this example. Set builder notation, recall curly brackets. We say that x can be any number in the set of, so any number contained in, that's that little e, the set of real numbers. Now, before I used a nice fancy R because the computer produced it, but here I'm going to, just to distinguish this as not any old R, we're going to do kind of a double thing there, make it a little fancy. So x is contained in the set of real numbers such that, remember the vertical line stated that, and then all we do is basically just write the inequality. We're like, well, x can't be any real number. Don't forget, it has to be less than 2. So now we're going to put the last two scenarios together, kind of combine them. Let's see what this says. So this says to graph, so negative 3 is less than or equal to x, which is less than 2. Another way of saying that is that x must be between negative 3 and 2. It can equal negative 3, so we'll put a closed circle there. It has to be bigger than negative 3, but it can't go up beyond, or it can't achieve 2 or beyond. So let's work with interval notation. So, all right, so x is ranging anywhere from negative 3 to 2. We put a closed bracket on the negative 3 because that can actually be achieved, and parentheses on 2 because it can't quite be 2. And set builder notation, squiggly brackets, x is contained in the set of real numbers such that, well, we just take the inequality and we write it again. So negative 3 is less than or equal to x is less than 2. So let's do some practice. And feel free in this slide to pause the video and try and write the two types of notation yourself before checking your answers. Okay, so for interval notation, we see that x can vary from just above 11 all the way up to infinity. So we write 11 to infinity, and always a parentheses with infinity, and also x can't be 11, so parentheses there to show it's not included. Set builder notation, now because we are dealing with real number lines, I'm going to not keep writing x is contained in the set of real numbers. It's kind of, if you're in this, working from this assumption, you can kind of leave that out. So, and what must be true? So x such that x is greater than 11. In effect, we just have to write the inequality for the graph. All right, let's look at this. So x goes from negative 8 up to 0. It's allowed to be negative 8, so we'll have a bracket, and it's allowed to be 0, so another bracket. So in set builder notation, we literally write the inequality for that yellow graph. So negative 8 is less than or equal to x is less than or equal to 0. This is an unusual one. We haven't seen this yet. Now, what you should know is that this statement here is kind of linked with an and between the two. It's really two statements. Is x is greater than or equal to negative 8, and at the same time, x has to be less than or equal to 0. This new graph is going to give us a different scenario. So let's take each part separately. So we have the arrow to the left where we have x is ranging from, whoops, what is that? Infinity sideways, from negative infinity to 4. We can achieve 4, but not negative infinity. And the graph on the right, the yellow arrow to the right, is from 15 up to positive infinity, and we can't achieve, x can't be 15. So we link this with a symbol U standing for union, and the union of these two intervals. So and the way that translates into words is it's an or statement. So either one, x has to be in one interval or the other, it can't be in both. And how do we write that in set builder notation? Well, we literally write the two statements separately. X can be less than 4, or, sorry, less than or equal to 4, or x can be bigger than 15. And you have to write the or, you can't sort of combine those two statements.
And finally, we have an interesting graph, very kind of similar to the one just above. So x can go from negative infinity to 0, but it can't be 0. So in fact, x can be all real numbers, right? But just not 0. Unified with, and then it can pick up on the other side of 0, be slightly more than 0, and go up to infinity. And in set builder notation, what I like about set builder notation is it's perfect for this kind of scenario, because all you have to write is that x can't be 0, and you're done. So we're going to end with two unusual scenarios. So here's a number line, and here's the graph. And you will see that there's no breaks in the graph, there's no interruptions. So in fact, it seems that x can span any real number. And in interval notation, of course, that would be that like this, that x goes from negative infinity up to infinity. And in set builder notation, you would just say, in this case, I will put x is contained in the set of real numbers, but there's no such that. There's no restriction. So we have that scenario. And the final example I'm doing just to show you some sort of a variation in set builder notation. Now, you will notice that x is not allowed to be sort of decimals, right? It can only be -2, -1, 0, 1, 2, 3. So in fact, interval notation is not going to be useful here, right? So that's not handy. It's only handy when we say when the graph is continuous. So in this second graph with the dots, it's a sort of discrete set of dots. So this is where set builder notation comes out handy. So, and this is where, doing this example to show you that x, in this case, it can't be a real number. It can only be an integer. And so we say x is contained of, and now there's a special symbol for integers. I mean, there's a special symbol for natural numbers, real numbers, all those things. I'm not going to go into that in this video, but it's a z that looks like that. So x has to be contained in the set of integers. And then you can write -2 is less than or equal to x is less than or equal to 3, because it's not any old integer it can be. So just wanted to show you that example to show you why we have to write x is contained in what set of numbers, because sometimes you're going to be in the set of integers or the set of natural numbers, and for that you'd have to specify.
Congrats, you made it to the end of my video. Hoping that means you found it helpful, and if so, please do like and subscribe, and check out more of my videos on my channel, Ready to Derive.